Hi folks, welcome back to 10.5 Polar Coordinates. In this video, we are going to take a look at two special types of polar graphs. One is called a rose curve, and the other one is called a limassol. We're going to start with the rose curve here, and we can see that there are going to be two different types. So one type is they're going to be vertically oriented, or go through the pi over 2 axis. And the other one is the horizontal one where we're going to go through theta equals 0. Okay, so let's see what those differences are. I'm going to pick a number for A and a number for N. So let's say that I have R equals 2 sine of 3 theta. All right, so if I have 2 sine 3 theta, let's see what happens. So this is going to be a vertically oriented rose curve, okay? And each petal of the rose curve is going to be 2 units long. And there are going to be a total of not 3, but there's actually going to be 6 petals. All right, so 6 petals that are going to be 2 units long. Now let's see what this looks like. If you graph this on Desmos, what you're going to get is a situation where you have one petal like this, you're going to have another petal like this, and then you'll have another petal like this. Okay, so you have a total of 3 petals. Now, because it's the sine, you know that it's going to go through this vertical line, okay? Now, you might be thinking, well, Judy, you just drew 3 petals and you told us that there were 6 petals. So it's 3 petals with an additional 3 petals on top of the ones that actually exist. So if I were to graph over this again, I would have the 4th petal, the 5th petal, and the 6th petal, okay? So as we look at it, there's only 3 petals, but what we really have is 3 petals on top of 3 other petals. Okay, let's take a look at what happens if I change this to be cosine. So if I change this to be R equals 2 cosine 3 theta, all right, what I'm going to get is I'm going to get 6 petals that are going to be 2 units long. However, they're going to go through this pole. So I'm going to start with my 1 petal here, and then I'm going to have one that comes up this way and one that comes up this way, and they should all be 2 units long. And on top of that, you're going to layer the next 3 petals. So petal number 4, petal number 5, and petal number 6, all right? So we have, so here's some basic rose curves, okay? And so let's write down some of this information. That the A value will tell us the length of each petal. Now, N, the number where we put in 3, that tells us almost the number of petals. So specifically, 2n tells us the number of petals. Okay? Some textbooks or videos might tell you that if it's odd, you're going to get only the number there. All right? So like 3 is an odd number, so I only saw 3 petals. That's kind of correct, except it's more accurate to say that there are 2 times 3 or 6 petals, but you only see half of them, okay? Now, whether the n value is even or odd actually shows us different graphs, okay? So if n is odd, then only n petals are visible. Okay, so if n is odd, then only n petals are visible. However, let's see what happens if n is even. Let's take a look, okay? So I'm going to erase these, and I'm going to go ahead and put in a different formula. Actually, let me just draw it down here. All right, so let's have sort of the outline here. And let's say that we're going to put in r equals 2 cosine 4 theta, okay? So when I type in 2 cosine 4 theta, I actually end up with not 4, but 2 times 4. I end up with 8 petals, and each petal will be a length of 2. And so we end up with 1, 2, 3, 4, and then 5, 6, 7, 8 petals, okay? So in this case, if n is even, then you're going to see, you see 2n petals. All right. Now, same thing if I wanted to see r equals 3 sine of 6 theta, there would be 12 petals visible, okay? But if I said r equals 3 sine 5 theta, because 5 is odd, I'd only see 5 petals. All right? So it's kind of neat. You should play around with that to see like how many petals you think you're going to see and what orientation they're going to be. All right? Now, let's move on to the last type of curve. All right, so this last type is something called a limassol. And we have special types of the limassons, okay? So just to highlight a few things, we have an a value in the front, and to that, we are adding b sine theta or b cosine theta. So the a and b values actually matter. The relationship between a and b matters, okay? So in this family of shapes with this particular function setup, okay, if I have that a and b, if that ratio a divided by b equals 1, okay, that's what you're going to get in this diagram, and this is called a cardioid, okay? So, for example, if I had r equals 2 plus 2 cosine theta, 2 divided by 2 is 1, so that shape is going to be a cardioid. Similarly, if I said r equals 3 minus 3 sine theta, okay, a divided by b is 1, I'm going to get a cardioid. So that is a special case of a limassol. Now, if you take the a and you divide it by b, let's use a different color. If I take a divided by b and it's between 1 and 2, then what you're going to get is a situation like this. And this is called a dimpled limassol. So I can tell here that a is 1.3, b is 1, so that ratio is greater than 1. So I end up with a small little dimple there. Another example of that might be r equals 5 plus 2 sine theta, 3 sine theta. 5 divided by 3 is between 1 and 2, and so I would end up with a dimpled limassol. All right. Let's see what happens if the ratio is greater than 2. So if a over b is greater than 2, what you're going to get is a shape that looks like a convex limassol. Okay? Convex meaning that there's no more dimple, there's no more divot, it's almost flat, okay? So if I had an equation like r equals 8 minus sine theta, 8 divided by 1 is bigger than 2, so I would end up with a convex Limassol. All right, let's take a look at some of these other shapes down here. So I've got my inner loop, all right? So when A over B is between 0 and 1, you end up with an inner loop. Okay, so that's this little guy right here. You have an inner loop inside of your Limassol. And you get that whenever you have r equals like 1 minus 2 sine theta. Okay, so 1 divided by 2 is a half. That's between 1 and 0. That would be an example of one that gives you an inner loop Limassol. Now, we have one last case here, and you'll notice that this should look familiar in that it's a circle. And yeah, when A over B equals 0, then you get a very, very special case, which is the circle. Okay, so we saw that earlier in the different video about circles and their formulas, but this is sort of the path of the Limassols, okay? Now, what you can see is that for all pictures that I've shown here, these are all cosine, 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 cosine. And cosine ones are Limassols that face side to side, okay? So let's just graph one cardioid. So let's say I had 3 plus 3 cosine theta. What that would give me is a cardioid, okay? And I know that because I have r equals 3 plus 3 cosine theta. So 3 divided by 3 is 1. So I'm going to end up with a cardioid. And it's going to be facing to the left because it's a positive. Now the 3 will tell you how far you go up and how far you go down. And then if you add them together to get 6, that tells you where the last part of your cardioid is. And then you can kind of connect them. And you end up with a cardioid. Okay. Now, let's try taking a look at some of the up and down ones. So let's say that I wanted to do one with an inner loop, okay? So let's say I had r equals 0.5 plus sine of theta. Now, if I graph that on Desmos, all right, so 0.5 sine theta, I should end up with a Limassol with an inner loop. And because it's the sine function, it should be facing down. Now, that 0.5 is important because 0.5 is going to be where it hits the inner circle, okay? So what I mean by that is that this inner loop is going to be, so it's going to go up to 1, but then I'll have an inner loop that goes halfway. And that's because A is 0.5. Now, I'm going to leave you here on the video, but I would encourage you to kind of play around with the numbers and see what other patterns you can find, all right? It's pretty fun to just kind of play around and see what you get and see what numbers change what. So have some fun with Desmos, and if you have any questions about polar graphs, come see me during office hours, and I'll talk to you soon.